Hi, my name is Phillip Clendenin, and this is the 5th lab for Physics 2212, Section P at Georgia Tech, and today we will be experimenting with magnetic braking with Faraday's law as we witness a bar magnet fall through a tube of aluminum foil. Before getting to the specifics of the experiment, let me delve into the important concepts that we will be using today. Listed on the screen, we have Faraday's law, Lenz's law, Biot-Savart law, and then we are going to be using general Newton's laws ideas that we have been using for the entire semester. Let me quickly cover each of these topics as they are crucial for understanding the rest of the lab. Faraday's law describes how an electric current produces a magnetic field, and conversely, how changing magnetic fields generates an electric current in a conductor. It also corresponds to the equation below it. Moving on, we have Lenz's law, which is basically the explanation or idea that a current produced according to Faraday's law, which we just discussed, is directed in the opposite direction to oppose the change in flux, and it also tries to exert a force that is opposite to the natural motion, kind of like the quote below. After this, we have Biot-Savart law, which is an equation that allows us to find the magnetic field of an object generated by a constant current that is generally uninterrupted. In this specific experiment, its main use is for calculating the magnetic force and field on both the current-carrying rings of the tube. Moving on to the more specific nature of the experiment, the data we recorded in terms of dropping the bar magnet through the aluminum foil was the time it took to fall through the entire tube. After getting the data, we are going to use the knowledge we have based on the equations from basic magnetic fields and forces, and then we're going to use the laws we previously mentioned to create a closed script code, which we will get to later on. When it came to collecting the experimental or manual data, I measured the length, width, and inner radius of the aluminum foil tube. We were also instructed to use the magnetometer app, which we used in past labs. In this lab, we were using it to find the north end of the small bar magnet. After having these easy and simple calculations for recording, all we have to do is record ourselves dropping the magnet through the aluminum foil for each of our 5 trials, and then we're going to go through the video, analyze how long it takes to do each drop, and then we're going to average our data and put it into its own row as displayed on the screen. What I observed during this experiment is that you could tell the magnet fell slightly slower through the aluminum tube comparatively to a natural situation or free fall drop through the air. My response to this was that there has to be a magnetic force within the aluminum tube that is pulling the opposite direction of gravity, so in the positive y direction. Using all of the information and knowledge that we have discussed in the previous 5 minutes or so, we created the closed script below. All of the produced outputs that came with the running of the code are related to magnetic field and magnetic forces, specifically in this case the bar magnet and aluminum foil. After displaying the closed script, we can continue to the discussion of the results as well as the difference in the results or percent error. Our calculation, we had the average to be 1.73 seconds, and then when we inserted our values into our closed script code, we produced a computed time of 2.111 seconds. And thus do another calculation where we do actual value minus experimental over the actual, we collect a percent error of 18.04%. Because the value is greater, I can announce an error to either my own MU or magnetic dipole calculation of the bar magnet, or there was a degree of human error in my calculations when I was timing the difference in the video between the top of the tube and the bottom of the tube. In this case, because I was a shorter time, it would have been me getting it early. When we look at the graph to the right, we can see that in the velocity versus time graph, we see a linear path at the beginning and end, however a flat section in the middle. From this, we can claim that at the early and late points of the tube, there was only force was gravity, however in the middle, the magnetic force of the tube was affecting it, and thus, because it is flat, we can imply there's a net force of 0. Finally, getting to the what-if questions, if the resistivity of the conductor were reduced practically to 0, the dynamics were changed in regards to a higher magnitude of magnetic force. Thus, because the magnetic force is higher and is opposing the direction of gravity, it would cause an even slower fall of the magnet. For the second what-if question, if holes were cut in the aluminum tubes, there would be less resistance because the natural created loops of the tube are not full or complete. Thus, there would be a current or magnetic force of lesser value, allowing the bar magnet to fall slightly quicker. That's all for today's lab. Thank you for listening.